Hello, my name is Ari Wahlroos. I work as a senior principal engineer here in the relay factory located in Vaasa, Finland. In this next presentation, I will give you details about our latest earth fault protection functionality applicable in compensated networks. And this protection function is called as multifrequency admittance protection. And this is the latest protection functionality what we have available in our Reliant series of protection relays. This presentation gives you details of the very latest commissioning of Ref 630 version 1.3 relays with multifrequency admittance protection here in the substation located here in Finland. This substation is actually 110 to 20 kV primary substation where the medium voltage network is compensated with a Peterson coil or arc suppression coil. This arc suppression coil is connected to the system through the earthing transformer. The coil and the earthing transformer is located here in the separate cabin. Our 20 kV bus bar and the base, there is 16 base of Ref 630 version 1.3 with multifrequency admittance protection. We use also abbreviation of MFA here. This multifrequency admittance protection in this case replaces the traditionally used I0 cosinus method and also any separate transient or restriking functionality which is traditionally required in order to cope with all faults occurring in the cable section. So with the multi-frequency function we can replace all the different fault type dedicated functions with a simple to set one function called as multi-frequency admittance protection. This commissioning test what we conducted, this was not an ordinary commissioning test because in the test what we conducted during 2 days we did very comprehensive evaluation of performance of this novel function. In 2 days we conducted 52 different types of earth faults in 2 locations here in these compensated networks. We varied the type of fault from continuous fault to restriking earth fault, which is very typical fault in cable sections of the lines in the network. In order to really validate the good sensitivity of multifrequency admittance protection, we varied the fault resistance greatly and we went up to 20 kilo ohms of fault resistance, which is very high ohmic fault. Such fault could occur in the overhead line sections of the feeders in the network. We also evaluated the performance of protection during various degree of Peterson coil tuning. So in this case, substation normally is operating very close to the resonance point, but in order to validate performance also in temporary cases when the coil is off-tuned, we also validated performance when the network is operating greatly in undercompensated mode, overcompensated mode, and even when the Peterson coil is disconnected. In this particular substation, many of the feeders here are actually composed of underground cables. But in terms of how much earth fault current each feeder produces, these feeders are quite different in that characteristics. For example, this first feeder introduces only very small value of earth fault current, 1.5 amperes. So it means that there is only few cables and mainly the feeder is composed of overhead lines. But in these two feeders here, we have much more underground cable sections, and each of these feeders then produce up till 20 amps of capacitive current. The total capacitive earth fault current produced by these 5 feeders, which were in our test setup, they totally introduce 50 amperes of capacitive current. And this current is then composed with compensated by the Peterson coil. Normally used compensation degree is slightly undercompensated, and the coil current is about 50 amperes. From earth fault protection perspective, there is a very important component in addition to the Peterson coil. There is the parallel resistor, which is typically connected to the parallel with a Peterson coil to the power auxiliary winding, typically to the 500 volt power auxiliary winding. In this case, this parallel resistor introduces about 8.6 amperes of resistive current when we have a galvanic fault in the network, meaning there is no fault resistance. In order now to illustrate and compare performance of this novel multi-frequency admittance protection, we evaluate a couple of real faults what was conducted during the commissioning test. As a first fault type, we look at a fault which was made in this feeder, and this fault was a fault on the cable section. It simulates a fault which may occur in a cable section of the feeder. So if a cable is damaged, the insulation of the cable is damaged like this, there may occur a very difficult earth fault type, which is known as restriking or intermittent earth fault. So in this case, you have a damaged insulation and arcing from the phase conductor to the grounded shield of the cable. And such fault was then simulated in a live network. And you can see it here.
3, 2, 1, 0.
So here you see how we conducted a restriking earth fault test in this network. And such fault is known to be very problematic with conventional, traditional protection algorithms, especially when they are based on fundamental frequencies, such as I0 cosinus method. The problem of this particular fault types comes from the fact that when we look what is happening at fault location with slow motion, you can see that this fault is very temporarily. The fault is in fact composed by series of very short duration of insulation breakdowns, and then during this time of insulation breakdowns, what protection sees is only very short duration of current flowing in the system. And here we can actually now see the inherent challenge of protection due to this restriking earth fault. Here we have measurement shown with red color from the faulty feeder, which should then of course trip this faulty feeder with the cable and a restriking fault. With the green color here is shown measurement from the healthy feeder, and you can see that during a restriking earth fault, such oscillation of quantities seen by protection is also seen in the healthy feeder. What we can here see is that during the restrikes here, you can see that there is only very temporarily current flowing, and the duration of actual fault is very short, typically only few milliseconds at maximum. And this very short duration of current spikes makes the system to oscillate, and this oscillation is seen in the neutral point voltage, and it's therefore seen in the whole substation, all the measurements, also in the healthy feeders. The problem of traditional method, and especially the evaluation of fault direction, is illustrated in this figure here. The problem is that the restriking earth fault results in highly oscillating quantities of current and voltage, and when traditional method such as I0 cosinus extracts fundamental frequency component from voltages and currents which are highly non-sinusoidal, the result is highly oscillating directional quantities. And this results in great risks of protection, selectivity and security. So you can here clearly see that the phasors measured both in the faulty feeder and in the healthy feeders are greatly oscillating during the restriking earth fault. And it makes risks of tripping of the faulty feeder, as you can see here, marked with the red color. So this phasor marked with red does not stay here permanently in the operate area. And similarly, there are risks of disconnecting the healthy feeder due to the fact that the phasor marked with green color does not stay here on the non-operate sector. The solution for such fault type is our multifrequency admittance protection. And multifrequency admittance protection introduces now a totally novel concept of calculating and evaluating fault direction with phasor calculation. In multifrequency admittance protection, instead of looking at these discrete oscillating phasors, we are actually introducing a totally novel concept of looking fault direction with phasor calculation. And this concept is called cumulative phasor summing. And you can see the benefit and the resulting great stabilization of oscillation in this figure. The fact and the idea of cumulative phasor summing is very simple. We have a neutral point voltage start threshold, and when that start threshold is exceeded, we start to build a directional quantity which is a cumulative sum of the phasors seen here. And you can see the result of this accumulated summing, cumulative summing technique here. So it provides a great stabilization of directional evaluation. Now you can see that we can, with very high security, we can see that the measurement of faulty feeder marked with red is in the operate sector, and the measurement from the healthy feeder stays here in the non-operate sector. Our function is called multifrequency admittance. The name multifrequency means that our function in fact is not only looking at 50 Hz or fundamental frequency. It actually is looking at frequencies higher than nominal, the harmonics. And why this evaluation of harmonics is beneficial and why we use that? You can see here that such a fault type of restriking earth fault produces these current spikes here. And through the Fourier transformation, we can see that each of these current spikes, they include a lot of harmonic frequencies. So the frequency spectrum of each spike here is quite broad. And actually, we can utilize this feature of this high frequency content of the signal in protection. And utilization of high frequency components comes from the fact that Peterson coil is actually tuned to 50 Hz. It cannot compensate for the high frequency components. And when we add these high frequency components to our admittance measurement together with the cumulative phasor summing, this is the result. We can achieve directional evaluation where our directional phasors in the healthy and faulty feeder are in phase opposition. If you recall theory of earth fault protection, such phasor diagram is obtained when you have an isolated neutral point of the system. And it means that at higher frequencies, the effect of the Peterson coil is not there. So our directional element based on multifrequency admittance calculation is essentially similar that you are getting in isolated system. And it provides ultimate selectivity as the phasors in the faulty and healthy feeder are in opposite phase opposition here. And our directional element is actually looking at these phasors, accumulated phasors calculated with multifrequency admittance and comparing it to the set threshold, which is a single boundary line, and the only parameter user has to set is this tilt angle here, which provides tilting of the operate sector. And this tilt is needed in order to compensate of the possible measurement inaccuracies, because the measurement inaccuracies have the tendency of turning this green phasor, so measurement from the healthy feeder, towards the operate area. So therefore, it is always recommended to have tilting of the operate sector to allow matching for the measurement inaccuracies, mainly coming from the measurement of the residual current with the ring core or cable core CT. We can also here see that how our accumulated phasor summing is greatly beneficial also here in the healthy feeder. When we compare the measurement of I0 cosinus component, you can see here that traditional method is highly affected by the oscillations due to the restrikes, but we can get rid of these oscillations with the accumulated phasor summing technique. Our function is called multifrequency admittance, and our admittance concept comes from the fact that with admittance we can obtain very good sensitivity of protection. And sensitivity of protection is especially needed when we are detecting faults in the overhead line sections of the feeders. So there could be earth faults due to the, for example, trees leaning to our overhead line conductors, phase conductors, and such fault tend to be quite high ohmic. And in this particular commissioning test, we simulated such high ohmic faults with high ohmic resistors connected from phase to earth. And we varied during the tests fault resistance from galvanic faults from step of 3 kilo ohm, 5 kilo ohm, 10 kilo ohm, and up to 20 kilo ohm. And let's now look how a fault with high ohmic fault resistance sees and looks from protection point of view. Here you see the waveform of voltage and current during a high ohmic earth fault. In this case, fault resistance is 5000 ohm or 5 kilo ohm. You can see that what fault resistance introduces to voltages and currents measured in the system. It introduces damping. So you can see that during a high ohmic fault, the magnitudes of both the neutral point voltage and residual current are greatly reduced. The concept of admittance protection is that the protection operation quantity is not only current, but it's the ratio of current to voltage. And this ratio is called as admittance. And due to the fact that fault resistance introduces damping both to current and voltage, their ratio actually is admittance, and this admittance remains constant. And this is illustrated here. So you can see we introduce a high ohmic earth fault. We know what is the value of parallel resistor of the coil, in this case 9 amperes. We can see that through the admittance calculation we can see this value regardless of the fault resistance value. And this is the great benefit of admittance calculation. So you can here see that this value of parallel resistor is seen in the faulty feeder through the admittance calculation. The challenge of traditional I0 cosinus method is the fact that as fault resistance dampens both current and voltage, and in case of I0 cosinus, especially the current, you can see that traditional method sees only very low value of I0 cosinus current. And it means that in order to catch such high ohmic fault, your I0 cosinus setting would have to be set very low value. And such low value then creates risks of protection selectivity if you then would have a restriking earth faults in your underground cable section of the lines, and fault would be restriking with high oscillation of fault quantities. But you can see here that with the admittance protection concept, we can, regardless of fault resistance value, always measure the value which is based on the value of the parallel resistor of the coil. And we have in the multifrequency admittance a settable current threshold, and it is then set very simply based on this parallel resistor value. In this case, our setting was set to 3 amperes when the parallel resistor in this case was about 8.6 amperes. And in the tests, we went even higher than 5 kilo ohms. We went to 10 and even 20 kilo ohm. And you can see that when we have a very high ohmic fault, 20 kilo ohms of fault in the system, it provides great damping to neutral point voltage and current. But through the admittance calculation, we can, by looking the ratio of current and voltage, evaluate the admittance which is constant and not affected by the fault resistance value. In case of high ohmic fault, high fault resistance value provides great damping of high frequency components. So in this case, multi-frequency admittance is based on fundamental frequency components because the high frequency components are dampened by the fault resistance. And you can see here that in such a case of high ohmic fault direction is very similar than with traditional method. But you can see here that with this novel concept of multi-frequency admittance, we can provide very secure protection for your cables and overhead lines regardless of fault resistance or fault type. And in case of any additional questions and concerns, so I recommend you to take a look at our white papers, what we have published on this area. You go to Google and type multi-frequency admittance and ABB, and you will obtain more information about this great protection function. Thank you very much.